Excellent. So it's really great to see you folks today. I'm really excited to share some thinking that I've been doing recently about where our production ML architecture is going. Let me just start presenting my slide. So I'm just going to cut to the chase and say what my conclusions were. So if you look at how production ML architectures have evolved, the way that I see it is that it's had a first generation, which is kind of like a fixed function pipeline. The second generation being a programmability within a pipeline of particular existing actions. And the question is, what's the third generation? And what I will assert is that we can use history as a guide to help us understand where it's likely that production ML architectures are going. And my assertion is if we look at the history of the evolution of GPU programming architectures, it will give us a guide to where the third generation of computer programmability and production ML architectures are going. And so after that, I'd like to introduce you to Ray and ask the question, is it possible that Ray and systems like Ray that make ML much more programmable, the next generation of programmable architectures? So my plan from here is just to quickly review GPU programming history and compare that with the evolution of production ML architectures. I'll talk about Ray and what it is, and then show how Ray is being used to build existing applications in a different way, but also enabling new applications. And I've left some time at the end for folks to ask me questions, so please don't, so I'm ready for that, and we'll have a few minutes at the end for Q&A. So I mentioned earlier on production ML architectures. And to be concrete about that, what I mean are systems deployed into production that operate at considerable scale. And I was tuned into the DoorDash presentation just before this. And as you folks saw, they were doing 7 million predictions a second peak, or 6.8 million. That's the type of thing that we're talking about when we're talking production ML architectures. One characteristic, as you saw just in that talk, is that they often require distributed training and distributed inference. And that distributed character is more or less universal now in production ML architectures. So what we're going to do now is dive into the history of GPUs. And this is a topic of some passion for me. And I'll try to keep it super basic, but I hope that it will provide sufficient insight for us to kind of see what the future might hold. So going back to the mid to late 90s, we saw the first generation of GPU programming architectures. And that was things like OpenCL 1.0 and Direct3D. And as input, you would have things like textures, polygon, meshes, that type of thing. And it would go through this pipeline of transform, clipping, polygonization, and then pixel operations. And finally, what would pop out at the end is this beautiful 3D image, right? And the revolution that happened with that first fixed function pipeline is that this was all hardware accelerated. And that allowed for basically the first time that consumers had accessible hardware accelerated 3D graphics. And that really massively expanded the possibilities. And that's what started the 3D gaming revolution with games like Quake and so on. The flexibility, though, came from the choice of the inputs. And there was a little bit of configurability in tweaking the pipeline, like, hey, where are the light sources and that type of thing. But the downside of this was you could not do complex effects. And if you wanted to do something more beautiful or artistic or creative within the limitations of that, they were out of reach from hardware acceleration. You got what you got with the hardware. If the hardware supported, I don't know, shadow buffers or something, then you got that. But if it didn't, right? So it was constraining to people. And that led to the second generation. And what I mean by the second generation now is that the pipeline stays the same, but you break the pipeline into sections with programmability within those sections. And some of you may have come across the term vertex and fragment shaders, and this is exactly what happened here. So vertex and fragment shaders are nothing more than small programs that run in hardware. And this is about the time of Direct3D, OpenCL 2, this started to happen. So they took that existing pipeline and made it more programmable. So to look at that, now you have a bit more flexibility, you have programmability within the pipeline, and these programs would be written in a C-like language. The two most popular at the time were the GL shading language and the high-level shading language from Microsoft. They were very similar, but from different companies and groups. But you still had to conform to the existing pipeline. So let me just go forward a slide and we'll come back to this one. This is what I mean. If you look at the formats between these different sections, it itself is pretty rigid, right? Like you have the vertices and geometry coming in here. Out of here pops vertices with a set of different properties that the vertex shaders have produced. And then finally, the fragment shader pumps out pixels at this end, also known as fragments, that get to the display. So these formats at these different stages are fixed. And that itself is where the limitation is coming now. But this is when we started to see something very interesting happen. This was the beginning of the GPU movement, that being general purpose GPUs. And so you can look at GPUs and those vertex and fragment shaders, and you know that it's Turing complete, right? Like every computation is possible in those vertex and fragment shaders, but there's a big difference between possible and easy. And so what happened is people started to write libraries for doing things like physics, but they were forced to take the problem that they were working on and make it conform to this weird combination of vertex and fragment shaders. And so I think that basically, it was a step forward, but it also indicated that people wanted to be able to code more generally for these things. And so as we mentioned, now you can actually go to a website and you can type in a small little program. This is just an example of the programmability for a fragment shader. And there would have been equivalent programs for vertex shaders. All right, now we come to the third generation. In the third generation, which examples of that are things like CG and OpenCL, is basically says, forget all of that. Stop worrying about pipelines and everything else. We're just gonna make it completely programmable. And when you think about that full programmability, you first realize that, basically the first generation and second generation pipelines, this is a superset of that. In fact, what happens is the first and second generation pipelines become libraries in this new system. And that kind of enables you to do some fascinating things. The interface now is just a programming language that for all intents and purposes looks like a normal day-to-day programming language with some extras for parallelization. And this really led to an explosion of applications. And this is what all of the modern deep learning infrastructure is built on, is this change that happened to complete programmability. And that led, to give you a chain, CUDA was another one of these early languages that led to CUDNN. Caffe was built on CUDNN. Caffe led to Torch. Torch led to PyTorch. And that's one of the most popular machine deep learning libraries available now. But you've heard me mention libraries a few times. And it's really important to understand this shift in focus, right? Originally, when you would talk to people in the games industry, they would be talking about OpenGL and Direct3D and writing code that runs on OpenGL and Direct3D. But over time, because of this programmability, this flexibility, people use engines like Unity or Unreal Engine 4 to kind of rate these games now. The GPU almost becomes a detail. And what this does is you've now taken that GPU and made it so that people without that level of experience of understanding pipelines and vertex shaders and fragment shaders and transforms and clipping can just use it like a normal code library. And that's really what opened up the GPUs that led to the Cambrian explosion of deep learning. And what's happened is no one talks about OpenGL now. Nobody talks, people do, but they talk about Unity, and OpenGL is just a way of getting to the compute, right? And when I say nobody's talking about, maybe that's a bit of an exaggeration, but just a little bit, right? So this is Google Trends showing, popularities of the term OpenGL descending over time and Unity increasing in popularity over time with a crossover around 2000 and 2010. So literally people are not worrying less about the architecture and focusing more and more on the characteristics and the libraries. So to give an example, this is code for doing a Mandelbrot fractal. Mandelbrot fractal is this very beautiful shape that some of you may be familiar with. And this at the time was revolutionary. instead of doing maths on the processor to work this out, you could write this tiny little program that didn't look much different from C. And all of a sudden it would be hardware accelerated. And all of a sudden you could do Mandelbrot sets at amazing resolutions in real time because of this. All right, so I can completely understand if some folks in the audience at this point are going, I came for a machine learning talk. Why is this guy going on about GPUs and all of this kind of stuff? And aside from our current machine learning revolution largely being built on these hardware accelerations that came from this previous generation, my assertion is that this can be a guide to history. And this can be a guide for us, right? Like history, one quote that I like is that history doesn't repeat, but it sometimes rhymes. And I'm wondering if there's a rhyme between GPU programming and where we will see ML production architectures go. And so when I look at this, I actually see surprising similarities with that transition. And so what I'm going to do now is I'm going to walk through the evolutions of Uber's ML production architecture. And I think you got some hint of the magnitude of that architecture from DoorDash's previous presentation, right? And that's, Uber Eats is just one small part of Uber. So you can imagine that the concerns there about ML architecture are even greater. And actually, as a side note, that's where I got to work with Mike and Jeremy, who were actually the founders of Tecton, the organizers of Apply. I was there as an ML evangelist while they were actually doing the hard work, not just opening their mouth, but actually writing code. So I'm going to use Uber as an example to walk us through this and their system, Michelangelo. But you can feel free to apply your other systems. I think it very generally describes a lot of the other production ML architectures that exist. So the first generation is described in an Uber engineering blog post from 2017 that you folks can look up. And this is a diagram from that paper that shows a pipeline, right? And it's the very standard pipeline that many of us are aware of, a little bit of data preparation, you put some stuff in feature stores, you have a batch trading job, you have a repository for models, you have offline training as well as online inference as well as offline inference. This kind of get data, train models, eval models, deploy and predict and monitor, right? Like this is very much the standard machine learning pipeline that we use for supervised classification and learning. So as I was looking at this and reflecting in preparation for this talk, I kind of looked at that and said, all right, that looks surprisingly familiar. So in much the same way that you get data, train models, eval models, deploy, predict, and monitor, you also have exactly the same thing. It reminded me of the GPU architectures, that very much fixed function pipeline. These are the stages, and the output is finally a classification. Instead of inputs being vertices, it's features, and the output is a prediction, right? But it had that same kind of linear progression character. Then we come to the second generation. And I was looking in preparation for this talk in a 2019 blog post. So you can see first generation 2017, second generation 2019. And they themselves described the first version of Michelangelo as essentially a monolithic architecture that managed tightly coupled workflows. And that they were finding that this was limiting what they could do and precluded serving of models. And so basically what that led us to do was to think about Michelangelo in a different way. We separated it out into components where, just like before, the interfaces were standardized, but you could put your own module in. And so this is a picture from that blog post that shows that exact same thing. So I'm going to flip forward and flip backward just so we can have a look at it. So this is a generation 2 GPU programming architecture. And this is the generation 2 Uber Michelangelo architecture. And you can see the similarities, right? They basically made it so that you could replace the first part of the pipeline with any of the standard tools that any of us prefer to code in, scikit-learn or Spark or so on, right? And then the second stage, the model training, again, you got this kind of library effect where it was pluggable and you could write bits of code. So I at least saw the similarity there and thought, interesting. So let's now ask, if mostly where we are right now is in the second generation, let's ask the question, what would the third generation look like? And what I would suggest is Number one, just like before, it can do everything that the first gen and second generation libraries can do, as pipelines can do. The interface is a programming language. At least in the case of GPUs, it led to an explosion of applications. So there's the potential here to have that same explosion of applications. And the key change is the focus of the shift to libraries, right? So you could argue then that the focus is now on libraries. The compute engine is just a detail now, just like you know, the way people started to think about writing games and so on was in engines like Unity and so on. It has the potential to open up power of machine learning to a huge number of users, and it moves the focus away. So you don't need to know what a P13 16x large EC2 instance is, right? You can, that's just a library function that you have to deal with. And so you don't have to worry about the details at that level. So that brings us to Ray. And what I would like, Ray could be considered as one of these third generation systems. Let me make the case, let me introduce you to it. And I'm not trying to shelve for Ray here. I am trying to suggest that there's a new way for us to think about machine learning, but Ray is a convenient example. And might give us hints about what we are going to see in terms of the evolution of ML production architectures. So Ray is basically a simple and flexible framework for distributed computation. And what makes it simple is that you make some minor annotations to functions and classes in, say, a language like Python. And all of a sudden, those same functions and classes can be deployed in a distributed manner. And what gives it the flexibility is that it's not a batch model at all. Tasks and actors can create new tasks and new actors so that you can have a more dynamic creation of functionality. And there's not a huge cost to creating a new task or a new actor. And that allows you to think about the problem in vastly different ways. The second thing that makes it up is that it's a cloud provider independent compute launcher autoscaler. So once you've described an application in Ray, it will then take that and kind of work out how to distribute it on your favorite cloud provider. And then just as importantly, and hopefully by now you have some intuition about why libraries are so important. It's an ecosystem of distributed computation libraries built on top of that API in the first case. So just to show it diagrammatically, you know, at the bottom layer, you have your favorite compute service provider, whether it's AWS or Azure or GCP or whatever, Kubernetes, whatever you need. You have Ray, which acts as an interface for these machine learning libraries to run on those particular things. And then you have a family of of machine learning oriented libraries. So there's some that are native Ray libraries designed from the beginning to run on top of Ray, but there's also a very healthy ecosystem of third-party libraries that includes many of our favorite things when we build ML models. Yeah, so that's kind of a quick overview of Ray. Ray's that little layer in the middle that that makes it easy for people to write distributed ML libraries and then takes care of the distribution of them across machines for you. So how does this fit with ML? So I think one way to think about it is this third generation is about making ML programmable and tackling the problem of programmability. But what we also discussed is that it moves the focus to libraries. So when you're using one of these libraries, you don't have to worry about the details about how the distributed computation is happening. You focus on the algorithm in much the same way that the third generation of GPU architectures allowed you to focus on the algorithm, and you now had a library of systems that you could use, just like folks shifted to Unity or PyTorch or whatever the library was. So with that, I'm going to take a moment to, you know, that's been a description of Ray. But let's evaluate whether it's actually being used in the way that we're describing, right? Let's evaluate whether it's showing similar properties to what we saw before. So I'm going to talk a little bit about 4 different ways that Ray was used. And the first is that it's going to be a simpler way to build first gen and second gen pipelines. As you may remember, that was one of the characteristics we saw, that the standard pipelines just become a library in that. The second one is as a tool to parallelize high performance ML systems. The third one is around making ML accessible. And you're starting to see the themes, like very much what we saw in the case of GPUs, we are now seeing in ML. And then the final one is this little thing about winning the America's Cup. So we'll get to that. So let's talk about its use as a simpler way to build first and second generation pipelines. So we mentioned earlier that one of the reasons to use this is basically you can implement existing systems more efficiently and allow for more sharing and distribution you get basically out of the box. So just recently, Uber basically shared its use of Ray to essentially show what Michelangelo 3 would look like, right? And what they said in their recent blog post was that it allowed them to treat the entire training pipeline as a single Python script. And that made it so much easier for them to work with and so much more intuitive. But what's even more interesting is that they themselves mentioned the concept of the ecosystem, the importance of libraries, and a standardized way for people to write machine learning libraries, both within Uber and also at the industry at large. So you can kind of see it show that thing that we talked about earlier, which is that the existing tasks that you're trying to do get a little bit easier. There's no, you can do the things that you can already do without too much trouble. It's just expressed rather than in the standard pipeline of stages, you just write it in code. So let's talk about the second use case now. The second one was really around high performance ML systems. And so there's a company using Ray called RoboVision, and they wanted to run a vehicle detection using 5 ML models running concurrently. And it didn't easily fit on a GPU. They could make it fit, but they had to cut their models. So they tried to just use standard Python to do it. And then even on a single machine, they were able to parallelize it using Ray and get a 3x performance improvement on the same hardware. And the thing is, I'll show you the code in a moment, or pseudocode for that. But I want folks to think about, if you didn't have something like Ray, how would you do this? Would you convert each ML model into a microservice, for example? It's definitely doable. I mean, it's not like this is the first time, someone's done stacked models, but just think about the complexity. So this is the basic pipeline of what they were trying to do. They were trying to process images and output classifications about what the vehicles were and what they're going. And they took each of these things and wrapped it in a Ray actor. And that gave them a lot of, an actor is just the basic primitive in the language, that gave them a lot more flexibility and especially gave them an accessible way to get to the GPU. And obviously I don't have enough time to go through the code, but it actually is surprisingly easy to do this, right? So this is the code. There's this little annotation at the top to describe a class called model. And then you have subclasses that you change the computation for. And basically what you do is in each case, you just specify who's next in the chain. And then you just feed the input to the first one, and then they land at the result collector, the thing that's actually capturing the data. So we took a relatively complex stacked model, wrote it in this way, and it can run on your local machine, but by changing the cluster that it runs on, all of a sudden it's distributed. And instead of trying to run 5 stacked models on one machine, you're running 5 stacked models on 5 machines, each with their own GPU. And Ray is taking care of all of the coordination and setting up those 5 machines. So a third example that I wanted to share was around making ML accessible. So there's a company called Descartes Labs, and they provide geospatial data analysis. And what people want to do, let's say that you are looking at images all over the world and you're trying to look at the ocean and find piles of garbage that have come into the ocean, right? Where is the garbage around the globe accumulating? So how they use Ray is that they create a simple interface like this, where you write a little bit of code on the left-hand side. You might be looking at a particular area. You develop your algorithm looking at that particular area, and then you click execute it. And for all intents and purposes, you can take all of the data for the entire world and run that same algorithm to identify all of those locations. And so what we see here is that Ray is enabling a small startup to analyze petabytes of data at their users' behest, and making machine learning and data processing more accessible, giving access to that massive distributed computing power. And so the final example that I'm going to give is undertaking ML projects that don't fit the standard ML pipeline. And so I want folks to think about things like reinforcement learning. And we had that very standard pipeline earlier on, but there are some things about that pipeline that kind of don't make sense for reinforcement learning. You may want to update your values and your behavior online. And so that means that you have a feedback loop. You're updating your model every minute, every 2 minutes, right? Those types of things are not so well supported in the pipeline. And so there's a lot of things that are not that simple. So what I'm going to talk about now is a company called Quantum Black, which is part of McKinsey. And they actually used Ray to build the algorithms that helped that team win the America's Cup. America's Cup is a big deal in the sailing industry. It's one of the world's oldest competitions. But here's what they did, just to give you some idea. They built an AI sailor using RL on RLlib, which is one of those libraries. And so they trained a reinforcement learning sailor. And then what they did is they trained a reinforcement learning boat designer. And the sailor was really strong and the boat designer was really strong. And now you can play these two things off each other, right? You can take the boat designer and the sailor, and the sailor builds a new, the sailor designs, the boat designer builds a new boat, the sailor tries it out. And this allows you to analyze 10 times as many designs as you would be able to if you had a human in the loop during the evaluation. And they themselves comment on it enabling them to run training jobs across dozens of systems with a few lines of code. And so that shows the potential there. But the question I'm asking is, if you wanted to build something like this on the conventional production ML architectures, and yes, they used quite a few machines to run these analysis, right? It does meet that property of inferences that we said earlier. How would you design that? What architectural support would you have? And this is what I mean by the third generation allowing flexibility and new applications at a distributed level that would have taken much more time if you had to code them natively. So in conclusion, the history of GPU rendering architectures might be giving us hints to where the ML production architectures are going as well. And so what we saw is that evolution from fixed function pipelines to evolvable programmability within the function pipelines to full programmability. And that led to a massive explosion. And Ray might be one example of these third generation programmable production ML architectures. And it's leading to new applications, simplifying existing architectures, parallelizing high performance ML systems, making ML accessible to non-specialists, and highly scalable algorithms for reinforcement learning. So if you'd like to learn more, you can look up the Ray framework. If you'd like to hear from companies like Uber and McKinsey that we talked about earlier, there is a Ray Summit coming up, June 22 to 24. And please don't hesitate to send me email if you have questions, and like many companies, we are hiring. And with that, I think we have a few minutes left for Q&A.
Nice. Awesome. So I've coagulated or congregated all of the questions that I found. First one up, how is OpenGL related to MLOps?
Ooh, how is OpenGL related to MLOps? I think OpenGL would correspond to something like cluster maintenance. And so maintaining that cluster, having ML people maintain that cluster capability and make those distributed machines. It's not easy to maintain a Kubernetes cluster with 1,000 GPUs in it, right? Like that's not an easy thing to do. And OpenGL made that easy, and I really appreciate MLOps making that easy for people working on machine learning.
Sweet. I like it. Right to the point. I like these answers, Waleed. So how does this compare with Dask or something like Metaflow, who coincidentally we're going to hear from right now in just a minute. So if you are interested in Metaflow, stick around. But yeah, how does this compare?
Yeah, so you can, so Dask can be thought of in a number of different ways. But one thing you can do, for example, and is being worked on and showing very promising performance results, is Dask on top of Ray. So you take the Dask system and replace the distributed computing layer of it, and then you can use Ray and still have the advantages of auto scaling, cluster management, all that kind of stuff being done for you. So it serves the same purpose in the sense of making distributed computing easy and accessible. It does it in different ways. And there's different choices there about the level of flexibility that you want to make available to users.
Have you tried Ray in a federated learning context?
Ooh, that's a really interesting one. We don't have much of a presence on mobile devices. Python in general doesn't have much of a presence on mobile devices, though Ray does support Java and C++ in addition, but most of our use is on Python. I guess in federated learning, we're talking about parts of it happening at the edge. It's definitely something that we've had some internal conversations about how you would structure that, but we haven't built anything out seriously or anything like that. But that's a really interesting application, and I think it would be, as I think about, there are some improvement. Like I'm already designing this in my head. I know how we do it, but it's not something that we've thought about architecturally how you would support in that federated learning model. But wow, what a great question.
Maybe it's a little spark of inspiration for you.
Thank you. So, reach out to me if you want to follow up.
Yes, there we go. I like when connections happen like that. So next one, and then I feel like we got to cut it short. And for everyone asking questions in Slack, I think Waleed's going to go over there after we cut him off on here, and he can continue answering all the questions. So last one that is pretty interesting for me too. I'm going to +1 this one. How does Ray handle observability?
Whoa, okay, that's a good one. Every time an actor, obviously this is something that we're trying to improve. There is a dashboard. You can actually, so we have a basic dashboard in the tool, but we're also continually adding features, and the community is helping us to continually add features to make understanding what's actually happening in the Ray cluster easier. So obviously things like tracing as well as observability, and understanding things like how much is this particular Ray piece using memory are things that are continually being improved. There's some existence there, but there's always room for more and to make things better. And there's also a Ray debugger. So that gives you some capabilities to actually dive in and explore what's going on.